My name is Nikolay Markov. I worked for Aligned Research Group, and some of you may probably been hearing my colleague yesterday talking about data stuff. So I will also be talking about data stuff, but more from, I think, more from engineering perspective. This a bit so about the code, about this library we all use in lab, which is called Pandas, and all that. So you also probably see the logo of PyData here. It's because also I'm also organizing events on the brand of PyData in Russia in different cities. So if you want to participate, also feel free to reach out and maybe give a speech or something. Once again, there's the usual thing for most of talks, which is like a shameless plug about me a little bit. So yeah, I said Nikolay, my nick is Enchantnerd, like pretty much everywhere in the internet. If you want to find me and to talk to me and discuss something, or say that I'm I wasn't correct describing some concepts and you want to correct me, I'm also open for that critiques. So yeah, I work as a principal architect in Aligned Research Group. I've been using a whole source of programming languages like Python, Golang, C, C++. I'm also currently using Rust, also using Scala, and so we can also discuss any of those if you're curious. So also I worked with different clouds, with Kubernetes, with container infrastructures, and so on and so forth. So as always, I usually add a lot of links to my presentations, and you can click and discover more information about the stuff that I'll be talking today. And the only thing is, I think I've replaced most of them with English links, with articles in English. Maybe some of them are occasionally pointing to some articles in Russian. If you find such case, feel free to ping me and to say that like there is something. Can you find some more material which is in some other language? So I can try and do just that. All right. So let me check if everything's working. All right, so we're very good here. So let's talk about issues that we may encounter dealing with ad hoc requests, like analyzing data stuff, right? So there is this picture, you all probably saw it on XKCD before. It usually was related to programmers, saying, so it's compiling, so it spent a lot of time waiting for data to be loaded, the model to be trained, results to be generated, and so on. For programmers, it was just compiling. So if I was speaking about some huge C++ project, for example, compiling that thing may take quite some time. But with data, there is also a lot of stuff that slows us down. Right, so especially if we're dealing with lots and lots of files that we have to, to analyze, to maybe somehow join together, to filter out bad entries from them, to, kind of prepare the whole thing. And a lot of people who came to this profession, they already realized this, ugly and sad truth about like 80 to 90% of the time data scientists works on data, he or she spends actually cleaning that data and loading it into an analysis tool, and then not the magic part where you deal with writing models and cross-validating and all that. So let's think a bit about it, and let's discuss what we can do to maybe make our life easier in that regard. I went preparing this talk, for the first time, I actually generated test data set. I used a Faker module. I think it's also Python thing, which you can use to generate yourself, kind of like time series data, for example, or something else. So I just decided to generate something like that. And I basically created 50,000 files, not very large files, but just general files, which is something, in my experience, kind of related to what a lot of data science people and data engineering people are doing as part of their jobs. So we have this data format, and what can we do with it? Well, I'm giving, I kind of put on my slide several small tips. Some of them may be pretty obvious. Some of you already probably know this stuff. Some of them may be a bit less obvious, but yeah, so it's just something that I've been really glad to discover when dealing with data pipelines using Pandas. So one first thing that I come up with is when you are cleaning the data set and preparing this data set for analysis, the fastest thing to do would be to not clean it in Pandas, to not do it in Pandas. I actually gave a different talk. I think this is one of the links which actually leads to a Russian version of things. I don't think I have my slides on that publicly available in English. If you are really curious, you can reach out to me and ask about those. But this is about analyzing the data at command line. So you can do some pre-processing of data in command line, which is really fast because we're using these tools which were written about like 20 years ago and are pretty stable and optimized and so on and so forth. So this is definitely worth a try, and we'll get back to it at some points on my next slides. All right, so we have this data set. What should we do with it? Obviously, the first thing to do is to read it, right? I mean, we have a bunch of files, so we have to read them in memory in order to perform some kind of statistical analysis, to train some model, or to do something else, like to draw some graphs over it. So okay, perfect is good. If you guys have any questions, feel free to post them on public channel. I'll be monitoring from time to time. So, but anyway, so let's continue. Okay, we need to read these not kind of crazy, but pretty big amount of files, and this already can become a challenge. All right, so I just went to Google and said, how can I read a huge amount of files using Pandas? And this is basically, one of the first links on Google's page, pointing me to Stack Overflow, which is, the place where you get all those good things for everyday work. So then this is the code which was there, but we have, we just take only all those CSV files which are not empty, which have size more than 0, and then we just use this generator to join all those files into a single data frame, right? So this is basically what this code does, and I think it's pretty straightforward, right? So we're just feeding it with a generator with all those files, and we use pd-concat to concatenate them into a single data frame in memory. Well, even though it's pretty obvious and maybe simple to understand, there is one more problem with this code. It's really, really slow. It's incredibly slow, right? And you can imagine why, right? Because even though we're dealing with those data frames on lower level, we have to allocate more and more memory, attaching these new things to the end of the data frame. And also Pandas says it in its documentation because it's optimized for column-wise processing, for in terms of Pandas, it's series-based processing, right? it's appending something to the end of the data frame is actually a pretty complex and slow procedure. So that's why it's pretty slow. What can we do without, or what can we do with it? Well, okay, we have several thousand of small files. Well, the obvious thing to do is let's just, for analysis, merge them all into one file, into one CSV file with all the logs where we can analyze it. And with Linux command line, I think the pretty straightforward solution would be something like this. And this seems to be reasonable to think of, with one exception. You know, actually, it turns out that Linux command line has those limits on how many arguments you can actually specify to a command. And that's what's happening there, right? Because when you use star, bash actually unrolls it to the whole list of files that you have in that directory and feeds them all as arguments to the program, right? In this case is cat. And if it turns out if we have more than like 4,096 files in one directory, then bash can't handle it by default. So this just won't work, even though it's a good first idea. Okay, so what can we do? What can we do next? Well, another pretty obvious and straightforward thing. Okay, so we can't do it in just one command. So why don't we, instead of specifying it as list of arguments, we just load it as an array of files and then just go over them and then just cat every file separately and then put them in transactions, right? So they just append with double greater sign. We just redirect the whole thing to the end of the file, appending new entries to it. Well, it's just a loop, a simple loop, and it should work in this case. The thing is, well, I mean, I already mentioned that files I've generated aren't so large, but it still takes it about 7 seconds, about actually 8 seconds to process the whole thing. I know probably to get, reliable results, I would have to run it several times. But on average, I think it was for me there about 8 seconds. So can we do better? What do you think? I thought about it for some time, and actually there is one more thing that we can try, and this thing is called GNewParallel. So maybe some of you already used that. It's a script written in Perl, and this script actually has a lot of research behind it. So about parallelizing things, about running a bunch of parallel jobs and doing several things in parallel. So that's obviously what it stands for. And turns out that because it kind of performs synchronization on line ends, we can do something like this. So we can run, in this case, -j stands for how many jobs you want to run. So we can run like 8 jobs simultaneously, running the same command with cat, appending entries to transactions. This probably won't be a perfect solution if you want all the entries in the file to be ordered, right? If you're analyzing some time series, but actually sorting things, this is something that you can do afterwards if you need to, right? And that's probably, if you're training some model, it's not something you really worry about, right? So when, to me, this whole pipeline just took about less than 2 seconds, like 1.5 seconds. And I think that's pretty awesome, actually. So I think that's a good way for joining things together, even though it's pretty obvious. And you can read more about GNewParallel there on the link that I have down here. So anyway, let's continue. So we have this file that's pretty nice, and now let's say we want to read some data from that file together with filtering it, right? So we have to filter out some bunch of things. We have to check if those things are falling into a list of categories that we want to read. And also you can see several straightforward approaches, right? So in this case, just for an idea, I also used gzipped version of that file because it's also, in my experience, it's a pretty often thing to encounter, right? So you have a bunch of gzip files on either on HDFS or on some other network file system, like clusterfs, Ceph, whatever, and you want to read them, unzip them, ungzip them on the fly, and then read them into the data frame for analysis. So when I'm talking to live auditory, I would probably ask you guys, what do you think is the fastest approach of these three, right? So we can read this thing into data frame directly with Pandas. Should be pretty optimized because it kind of has to perform it in C code, and then we are just filtering that data frame and generating dictionary from it. I'm outputting dictionary here because this is the output of basically all these three functions. So we're outputting a dictionary of things which we can then translate to data frame or not to translate to data frame, depends. In other two examples, I'm actually using standard Python library thing. So I'm ungzipping this file on the fly. I'm using buffered reader in both cases, and then I'm just filtering those lines using a regular for loop, right? So I'm just checking if that entry is in our set of entries that we are looking for, and then we just append these things to our data set. Okay, so maybe anyone has any ideas? Which one is faster? But so obviously the reason I put this slide here is because it's something of a surprise here, right? So actually the Pandas version, which is the shortest one, which seems to be we just rely on that hidden machinery for doing a lot of filtering and loading and all those things for us. It actually takes about 5 minutes to complete. So it's crazy amount of time. And the thing is that even just regular for loop, when we are checking this thing on every iteration, it just takes 10 seconds instead of 5 minutes. So it's faster by a huge margin. And if we are a bit more clever about checking the condition there, so we're checking it one level up, so we get even faster. So we can have like less than 5 seconds instead of 5 minutes. And I think this is pretty awesome. So you can read about experiments around that also on this link. And even further, when preparing this talk, I also found a pretty outstanding research on GitHub with the guy who was comparing different ways of reading the data into Python, basically. And turns out that Pandas' way of reading things is one of the slowest. So you may really consider reading the file without Pandas first, or filtering it outside of Pandas first, and only then converting it to a data frame to work on, right? So also feel free to discover things. We don't have enough time to cover all the details here, but yeah, just if you think that Pandas is really fast about this kind of processing, so you may consider other options too. All right. Yeah, to dict method will need some time, obviously, but I mean, it's still. I think I checked that, and to dict doesn't really make it a lot faster. So I won't be able to test it with you right now. I had this notebook somewhere, but I won't be showing it today, unfortunately. So you can test it, and also you can read the link. Yeah, or I see I mentioned some. I left some Russian words here, so I'm just asking which is faster. Sorry about that. So you can read this link, and you can read this link, and you'll see what's real different there, and what are the suggestions that were used while reading those data sets. Okay. And there are some cases where you actually depend heavily on some complex logic for filtering. And I agree that sometimes it's pretty hard to do it, without loading it to Python first. Because instead of that, you'll have to either use some other crazy tools like awk, which I highly recommend, but I also get the idea that it may be hard to deal with. So there is this really handy method called from records in Pandas in data frames, which you can use to actually feed it with a generator. And inside that generator, how just Python generally works, you can filter out all the things, all the possible way you want to. Right, you can write any function, any predicate, which will select those rows, select those entries from the input data set for your data frame. It won't be really fast, obviously. It will be slow, but if there is a pretty complex logic to which you need to use, you can consider using this method as well. And another thing is, I decided to not remove this slide because, I mean, it's pretty. I think it's a bit obsolete already to this day. But anyway, it's probably obvious that when reading data from some data source, it's usually a good idea to use a buffered reader for that, right? So you read data in chunks. And then just encode them in memory into the format that you need, right, to convert it to some structures of your language, Python or some other. And actually for quite some time, I think now it's a default option, but for quite some time in Pandas, they were using a different mechanism, and this chunking mechanism was something that was like a better version of things. So now I think this low memory parameter to read CSV is enabled by default. I just left this slide because it should be pretty obvious, and you already, if you are using some other tool than Pandas to read the data, and you don't have much memory, so you can think of this thing. Maybe some other tool, they don't have it enabled by default, and you can use it for your purposes. And another thing with chunking is that I know that we just merged several thousand of small files into one big file, but obviously if you don't have enough RAM, you will probably consider reading this data still by chunks. Right, and in Python, in Pandas, there is a way to do that. It's also a pretty good link to read through. It's about, so where read CSV, you can specify this parameter called chunk size, and instead of a data frame, as a result, it will give you an iterator over data frame. So it will lazily load the data from the disk, and you will be able to process each data frame, each next chunk independently. So it's kind of pretty obvious to use that approach, but I was surprised that not a lot of people actually know that you can do that. not a lot of people know that it exists. So I just maybe help somebody. All right. So now we loaded this stuff into memory. Let's think how we can deal with it, how we can digest it. So we're just, as we mentioned, we can just read this using read CSV, and this is pretty nice. We see that the size of a merged CSV file, well, in my case, it was about 70 megabytes, 700, about 800 actually, 800 megabytes. And I thought, well, it's all right. I mean, I have plenty of RAM on my PC, so what could go wrong? So I just loaded this data frame into memory, and when I checked it, you can actually use .info with memory usage deep for that. It just gives you more more precise results based on the types you use in your code. So, and it was about like 2 gigabytes of RAM just consumed by that data set loaded into memory, even though the file is like less than twice smaller. So what did go wrong? Well, first thing first, turns out that Pandas, when it sees integers, by default, it just considers them in 64s. So, I mean, we can use any kind of tool to check the range that we need to deal with before loading the data, right? So we can look at the column and check, okay, we have like numbers from 1 to 150, 100, 150,000, or we have like, just 100,000. So obviously, if we check that, it seems a good idea to actually use a smaller data type, right? And we also can notice that we don't have any negatives, so we can use unsigned type also for that. Okay, so I even did a more comprehensive check here, as you may see. You can on a data frame, you can do a downcasting to another type, and you can also recheck how much memory it consumes afterwards. And we see that it consumes about like half of that. Well, that's expected result, right? We are using twice smaller data types, so we are using twice less memory. All right. So I was quite happy with this solution. So I just specified data types explicitly. By the way, when I was preparing this thing, I was using. It turned out I actually used pre 1.0, 1.0 Pandas, which now has string type. But anyways, so I specified 2 in 32, and I was expected to, that my data set will use a lot less memory. Well, not quite, really. I mean, it was 1.7, it went to 1.6, so it didn't help much, unfortunately. All right. But, well, obviously it would help a lot if my data set was consisting only from numbers, right? Only from integers, especially. But, okay. So what are other things that we can do? Let me... Okay. Yeah, so I see lots of one guy is recommending VEX library for reading CSV files, which is a lot faster than Pandas. I actually never tried that, but thanks for pointing that out. I think we can, people who are also listening or interested in this thing can go and try it as well. All right. So what seems to be the culprit here? And I saw that even though the column inside the CSV that I loaded was actually a date time, by default, Pandas, by some reason, didn't recognize it. Right? Pandas actually has a built-in date time type, but turns out it can't always recognize it. And in this case, you can actually specify it explicitly. So you can specify the date parser if you know that format, And probably if you're just joining your logs from, different, even from different files, you probably still have the same format for the date, right? At least I hope so. Maybe it's even more complicated in that case, but anyway, so you can actually specify a custom date loader when reading the data frame. So you can specify date time, strp time, whatever, you know this function, you can specify the exact data format. And then when the data frame is read into memory, you see that it actually is a lot smaller. So we went from almost 2 gigabytes to just 1 gigabyte. And I know that in this case, the whole loading takes a lot more time, but make sure that you are specifying the format if it's the same for all the records in your data frame, because otherwise Pandas will try to guess that format for every single entry using datutil, and it will be even slower. And of course, it will handle the cases where you have, different date times there, but I mean, different formats for date times. But well, that's painful. Okay, so we went down to 1 gigabyte. Another thing is that I was actually quite thrilled to learn that in Pandas there is also a category type. Right, so if you have a numeric column which sole purpose is to encode some categorical value, you don't really need to encode it to be, int, even if it's in 32 or in 16 or anything. You can just use a category type in Pandas as well. And if you do that, if you just encode the column as a category, if there are not so many categories there, you can also get memory usage decrease. And also it will simplify some things for processing category types inside Pandas for you. So also it seems to be pretty obvious, but it's actually surprising that a lot of people didn't know that before I told them that such thing exists. So it's helpful sometimes to read, change logs and follow that. All right, so let's speed things up a bit. Okay, let me check if there are any more comments there. Okay. This is also pretty obvious thing, but you know that, well, usually it's a whole other topic and it has a lot of additional underneath magic there. But when you are dealing with data stuff in Python, and especially NumPy, which is like underneath both Pandas and most of the data science Python infrastructure, so it actually is usually compiled with some kind of BLAS optimization. BLAS stands for Basic Linear Algebra Subprograms, and you probably know that if you ever were interested in how it works under the hood, you probably know that there is, OpenBLAS, there is Atlas, there is Flatpak. There are different kinds of performance frameworks for macOS or Windows, which you can use, which will definitely give you a speed up compared to just regular code, regular software approach. So how does it work? I mean, obviously, you can read all these links. You can read about that. There are several implementations of BLAS. There is Intel MKL, which is supposed to be faster on Intel processors. Spoiler ahead, it's not really. I mean, currently, open version of OpenBLAS, it's pretty comparable with Intel MKL. And it really depends on the task, but generally, it doesn't worth the effort dealing with Intel MKL. But anyways, so the way it works is actually your CPU, which has a whole bunch of additional wide registers for processing several entries instead of just one entry. This is not just, well, it all started with MMX registers in Intel back in 1998, I think. Afterwards came SSE, SSE2, SSE3. Now we have AVX, AVX 260, 256, and AVX, even AVX 512, right? So, well, if you're running this code on a modern CPU, BLAS helps you to use all those optimizations for your code to run faster. So if you see that for some reason your code, your NumPy-based or Pandas-based code is running really, really slow, just recheck whether you're using the version compiled to some kind of optimization like that. So whether you have OpenBLAS installed or you have MKL installed, whether NumPy is built with support for that BLAS implementation that you have, and so on. So also, it probably is really obvious, and you can actually do it in NumPy itself. So currently I don't remember how to do that. You can just import it and ask whether it was compiled with NumPy, with some kind of BLAS. But I think in one of those articles, definitely there is a way to check that. So what else? Well, it seems pretty obvious. Yeah, sorry, I think I don't have much time left, so I'll try to be pretty quick here. It seems to be pretty obvious that if you have all those vectorization things that can help you speed up things a lot, it definitely doesn't worth it to use just regular loops over your vectors of values, right? So, and also it was quite a surprise for some people that, for example, apply isn't actually a vectorized function. There is no vectorization happening there. It just basically runs your function in a loop, like iterals or itertuples or a lot of other things do. And it's just the fact that it's a C loop and not a Python loop, it doesn't really help. So you can compare different versions of things. Obviously, the regular for loop is the slowest of them all, but apply isn't much faster, and it's kind of clear that vectorized solution will be a lot faster. You can also read about it in different sources and different links I have there. Also, it seems also quite a surprise to me when it was quite a surprise to me when I dealt with it, when I encountered it, that Pandas series, it kind of it seems to be just a thin wrapper on top of NumPy and DRA. Just the fact is it's not, right? So it does add a lot of helpers and cleaner API for you to deal with vectors, but actually running a function over a series, over a vector in Pandas way of thinking, and just over a vector in NumPy way of thinking, which is in DRA, can bring you incredible speed up, right? So you can see with running the same function over series is about like more than 4 times slower than just running the same function over in DRA. So this is also something to consider if you want to optimize. All right. There are such cases where there are multiple conditions, and a lot of people also think that this is definitely some of the cases where, I'm just checking the chat here. There are some cases where you just can't optimize things further, right? So if you're if you're experimenting building your own decision tree, for example, so you have the whole bunch of these checks and you're seeing whether it works good or not, you can, do something like that for classifying. And I mean, it works. Even if we learn that apply isn't vectorizing anything, it works. We can, just split things to classes using this very simplest decision tree mechanism here. But actually, even though it has several conditions here, Pandas also has a pretty good helper for that. So we can just split the data into bins, which is a basic statistical thing, and we can also label them. So this code, it does pretty much the same as this code on top of it, but it does it almost twice as fast. So this is also something that you can use to deal with these, cases where you have to apply a bunch of conditions and so on, instead of just also going over the loop and running this if in Python. You can do that. And and also one of the questions I'm asked often when giving my lectures to students is, how the hell do we process Python Pandas data frame in parallel? How do we process rows in parallel if we can't vectorize things for some reason, for example? I had one of those things where I had to parse URLs, and this is something that is really hard to vectorize. So I've been using some approach like this with concurrent features. You can actually use process pool executor and process every row separately in separate process. And there is this really, really awesome library called TQDM, which you can use for drawing you a full-featured progress bar. On top of that, inside your Jupyter notebook or in a console, in terminal. But we also mentioned GNU Parallel today. So to CSV and GNU Parallel can be even faster than this approach. So if you have just a text file and if you want to process a bunch of things in parallel, feel free to just write a Python script for the complicated part and then just run this script in parallel for all the lines in your data frame. And I think this will actually be one of the fastest ways of doing that thing for processing rows in parallel. Okay. So, and going back to the slide where I said that you shouldn't just write plain Python fors and play Python loops for processing data. Well, there are some cases there it actually works. It works sometimes when you are processing not really huge tensors, not really huge matrices, because NumPy is optimized for dealing with huge data sets, right? And for smaller data sets, all those wrappers and all that magic that it drops on top of that, it kind of gives you a bit of an overhead to deal with. So NumPy, with its JIT-based solution, where you can just write Python code and then you just wrap it this function into a decorator with mjit, it actually helps a lot more in this case. So you can get, even though it's just plain Python code, NumPy optimize it to be more vectorized, so it may run even faster than NumPy in some cases. You can read about NumPy. You can also try using different compilers for Python code or languages like Cython. There is also a thing called NuItka for compiling Python code into C++ code and then compiling C++ and so on. So it's pretty, it's more hardcore ways of optimizing things. And I know that, for example, one of the projects that use this approach with Cython is Word2Vec with the implementation that used to be part of GenSim. Right, so in GenSim, Python library for NLP, the implementation of Word2Vec, I'm not sure actually if it still uses Cython, but one of the first editions, it used Cython, and it was one of the fastest implementations of Word2Vec on the market back at that day. So it's pretty awesome. All right, and that's, I think I kind of broke the time limit here. Sorry about that, but that's all that I had to tell you for today. I think I totally agree that some parts of the things that I talk about today were pretty obvious, and you probably, knew it a long time ago. But I hope that for some people who are starting to use Pandas for data analysis, starting to experiment around, and who want to perform these experiments locally on less powerful machines, this may be, yeah, something happens there. This may be helpful, to say hope so. So if you guys have any questions, feel free to ask.